Hi, in this video I'm going to tell you a little bit about ARM's real-time server and how it works and why it's so fast. The new ARM's real-time server is dependent on something that we call an in-memory data cube, which means that all the results will be placed in the memory cubes so you can access them. And before calculating, they will be run through are what we call the Hierarchical Calculation Engine, the HCE, which is technically directed acyclic graph, a DAG, that we have implemented specifically for ARMS calculations, risk calculations and aggregations. It's not multi-purpose, totally general, but it is designed to aggregate risk numbers very fast. So what do we get from this in terms of features? Well, the hierarchical computing engine can be used and run in parallel. So if you have this on a big server, the calculations can be done bottom up using all the service resources in parallel. And secondly, the results, the in-memory cube, can be accessed by multiple clients at the same time using the same memory. So everyone that connects to this result set will see the same thing. And if we update that memory cube, then everyone will get a push message that the results have been updated. Further, there is we accept changes on multiple levels of aggregation. So it's possible to alter positions at position level, but it's also possible to hijack information on results level. So you can insert your own P&L samples or calculated market values or anything else higher up in the hierarchy. So, and that would fire off and trigger an alternate aggregation above the level where you insert your own information. And from a user perspective, we have minimized network load in terms of how much information is sent from the server to the desktop for the user, in terms that it will only send the information that you're actually browsing on your PC. So if you have a vector of 1 million data points, we won't send the 1 million as you're not viewing the complete million, you're just viewing the first 100. And everything in the server can be accessed using an API. We use an internal API, socket-based, for our clients, our thin clients, but the users can also develop their own clients and viewers in, for example, Python with the same API. So that's the real-time server and the feature set. Let's have a look at what this actually, what's happening in such a hierarchical calculation engine or this DAG. So I've made a sort of a Excel mock-up. Excel is actually a graph. So this is a good example of how a graph and what the feature set of this is. So let's pretend we have a vector of positions, position data, that's the bottom level of this graph. And then on the position level, we have multiple attributes, which means that we can access we can aggregate on different attributes and things like that. So say here we have portfolios that aggregate these positions. And then we have the next layer, which is some form of transformation that goes from the position to some sort of number. And here in this Excel sheet, we've just taken the length of the string of the position. Obviously, in real world, this might be a calculation of the market value or P&L samples for the historical simulation or something like that. And then on the next level, you have the hierarchy itself, the aggregation bit. So these cells now aggregate from the transformation from the lower level and aggregates all the way up to the top. Um, and the graph, it's what it is. It's actually both the formula. So if we switch to formulas, then you can see that the Excel sheet stores the transformations. What is the task to be done on lower level in the graph? So the actual formula or function is defined in these cells, and it's the same with the ARMS risk graph. It has the formulas for calculating value at risk and P&L and things like that. And the aggregation is also stored, how to aggregate from cells below in the graph. So with these two together, we can then see that if we change something at the bottom level, the number of cells, it immediately recomputes along the path for which it becomes dirty. So if we change something at this level, it will only recompute the numbers that needs to be recomputed, and all the other numbers are just untouched. So we get a new top node result from changing something at this level. So this is how this works. This is how a risk engine would then have an alteration to a position, or it becomes you during the day you trade, you get a bigger position, you recalculate the P&L samples for that position, and then you aggregate that into the whole set of information that you present to your users at the most efficient way. So this is the so-called directed acyclic graph that we coined our hierarchical calculation engine. So this is the workhorse behind this. So let's see how this looks in the ARMS terms. So I'm going to switch down the Excel, and then let's have a look at what we're doing. I'm just going to show you. We have makeup banking position. It actually consists of 700,000 positions of different types. So you can see that we're not making this up when we do the calculation. So you have 53 different position types that are actually calculated in this server. And these are the number of positions per instrument type. So you can see we have 56,000 interest rate swaps, and we have 400,000 FX forwards in this mock-up banking book. So let's see then on the calculation bits. So here we have started the server. It has already calculated. We can see that it started reading the positions, and then a minute later it started doing the PVs, and then 2 minutes later it's calculating VAR, historical VAR, and then when it's done, the memory is full, and then it's waiting for connections from clients to access the memory cubes. So we're talking roughly 2 minutes to do 700,000 calculations for 250 historical days for one date. So the calculation bit is quite fast. Obviously, first time it has to calculate all nodes. And then we can view the results. So this is then the ARMS client connecting to this result set. So on the top node, we have a very big number for the market value and also a big number for the historical VAR. So we can then split this down on some sort of a location hierarchy. And we can see we have Asia and Europe and US and the market values and the VAR. So what are the benefits now of having this memory cube? Well, as we can re-aggregate so we can do simulations such as moving a portfolio. So let's say we want to do a Brexit scenario. So we're going to move the London desk to Asia. So we can then grab all the positions and portfolios in that and move it to Asia and ask for a recompute. And then we can see the cells that became dirty, that changed all the way to the top. Well, obviously the top is the same because it still aggregates to the same total risk on the top. But Asia just got a lot more riskier when we moved London into Asia. And then we can also go all the way down on position level. So we can say that, okay, let's say that we want to recompute this particular position only. So we can now see that we have a position in a swap, and we can just set this to 0 and see how that affects the global position. So let's simulate that. And then on top of the fictitious move of the portfolio, we can see that this portfolio level, as this was a hedge, raised quite considerably. So now we recalculated the whole tree above this node all the way up to the top. And the top changed, but it changed so little that you're not seeing, it's not even a percentage change because it was such a small position. And then this is the benefits of having a hierarchical tree graph that runs underneath the risk calculations, because then once you get new positions coming in through the day, it will recompute and send the new levels out to your viewers, and you can also then play around with that data in your private space. So this is how to understand the new ARMS real-time server and the underpinnings using the hierarchical calculation engine. Thank you very much.